Hi everybody, my name is Lincoln Austin. I'm just going to do a quick demonstration on an AGA orifice plate sizing. As you can see on the screen, we have the CONVAL toolbox. This has a number of tools in it, one of which is the differential pressure flow element. It's also got thermal wells and thermodynamics, and I'll touch on the thermodynamics shortly. So if I just open the differential pressure calculation. So we have the differential pressure flow element tool. Down the left hand side we have different sections with subsections, and as you can see, as we click on each section the window changes. I'll leave that on medium and pipe. Very quickly, over on the right we have a dynamic help file. We've got an overview of the calculation, we've got the uncertainties, and you can also create some graphs using any of these tools down in here, but I won't be demonstrating that just now. So in here we can give it an identifier, and I'm going to call it DPF, DP flow. I'm going to call it AGA 8 orifice plate calculation, and we can give it a tag number. So we'll call it FE 001 DPF. There are a number of expansion arrows, and we can expand out each section as we want to. I'm going to very quickly just demonstrate the AGA 8 calculation. So I'm going to select the medium. There's a number of pre-built functions. Under fluid mixtures, I'm going to choose my natural gas AGA 8. That selects the calculation method, and I have already pre-populated AGA 8 gas composition. Here you can see I've just selected that. If I create new, it pops up with the same window as when I click edit, and you can then enter these parameters and mole percentages, or you can do it by mass or volume. You can also, if you don't end up with 100%, let's say there's 99.8, you can normalize it, and then it will adjust all the values accordingly. I'm just going to click OK, and now my gas is populated into the calculation. I choose an operating pressure of 20 bar, 15 centigrade. You can globally change all your units here, or you can change them individually. I'm just going to change this one to bar G. You can see our operating density there has been populated based on the gas composition, and there's various other bits here like the sound velocity and the isentropic coefficient. Same situation, click the three dots and you can pull up a whole load of different pipe materials, very extensive database. I'm going to try and keep this video short, keep that code drawn. I'm going to go for an ANSI. I could have clicked on those three dots, it would have pulled up the same display here. I'm going to go for a 6-inch shed 80, and we can see we've got an error. We'll go class 300. I'm just going to change these units to millimeters, and hey presto, our pipeline is now specified, including the linear coefficient of thermal expansion. We can globally expand all these and shrink them. If I go to a flow element, assuming this is a Daniels carrier, I've got concentric square edge plate, it will be a flange tap. And I'm going to type in 316 for the orifice plate material. I'm not going to populate the edge radius. Just popping down to differential pressure, I'm going to assume we've got 250 millibar at a volumetric flow rate of 20,000 cubic meters an hour. Incidentally, the standard here that I am using is 0 centigrade and 1.013 bar absolute. We can change that if we want to. You've got a whole different range. So if you want 60 Fahrenheit and 40.5 psi, I think it is, you can select that. So we've actually now selected our plate size, and here is our bore calculated based on our gas, our volumetric flow rate, and the differential pressure we've requested, and that gives us a beta ratio of 0.66. Here we have our outlet condition, outlet and inlet straight lengths of pipe for 0 additional uncertainty, column A, and column B shown there for your 50%. I can change that to factors of pipe diameter. We also have some uncertainties here. I'm just going to assume you've got absolutely perfect measurement. You're taking this digitally, and we have differential pressure is going to be of span, so 0.025. We've no density error, so because you've got perfect GC, and that gives us an error here of mass flow error of 0.829% of 20,000 cubic meters an hour at full scale. We can extend our uncertainties. We can also plot this as well, just by clicking on that. I'll show you that at the end. We can show the sensitivity coefficients just by clicking the extend uncertainty calculation. We can also put in our error of temperature. Whoops, if I make that 0.5, and again we'll use the Schneider Electric 0.025% error of reading transmitter for our pressure transmitter. Just has a slight impact on the error of full scale. If you wanted to plot the error over a flow range, just open up a graph, select the parameter, flow rate, let's say 2,000, 20,000, update that. And so there is your classic bell-mouth shape error curve. And what we can do on the graph is we can scroll up and down. You can see these two parameters changing. You can see your error statement changing. So if we've got 20,000 full scale and come down to fifth of scale, still better than 1%. If we go down to 2,000, we are at about 1%. That's a 10 to 1 turn down. We can save this graph. If I close that, it will ask me if I want to save it. Click yes. The other thing we can do on here, if I go to the element, is we can have and put in 3 operating points if we want to. I've just shown you how to graph it, but we can put in 3 operating points as well. And for example, we should just be able to copy that information across and put in, I don't know, 10,000, put in 2,000 on the next one. See our differential pressure populated, and your discharge coefficients are shown. That's a very quick way to show you how to do an AGA 8 calculation. Incidentally, when you save these, it doesn't save to a database, it saves to a file. So if you had a problem and wanted to contact support, the support desk is extremely proactive. We get back to people very, very quickly. We can email support just by clicking on the question mark, clicking on email support, and my machines are acting a little slow. You can see an email populates. You can type in your details here. You can put your signature, describe the problem, issue with CD value, for example. Maybe you just need a bit more explanation on it, and then you can just send it off. So it sends off just that calculation, not the database. It also takes a screenshot and a little bit of system information, and then you can just click send. That is how you do an AGA 8 orifice plate sizing calculation using CONVAL from First. I'm not going to save that. I'm just going to show you something else very quickly in the thermodynamics section. If I click in the thermodynamics, we can actually also populate the AGA 8 gas separately in here. If I click on medium, we'll get my machine's acting very slow today, I do apologise. Go to fluid mixtures, AGA 8 gas, and we can go and click on the mixture composition, Click on the, as I did before, we click new and type one up. Brings up the same window as the AGA 8 gas composition. We can normalise it as explained before. If I just click OK there, and I can put in 20 bar, 15. If I just change that to centigrade bar G, and hey presto, all the rest of the information's already there. I hope that was useful. Thanks very much for watching.